Hi, today's topic is field effect transistors, FETs, and we are still using Group's Basic Electronics as our reference book. A field effect transistor is a three-terminal voltage-controlled unipolar device. They depend on one type of charge carrier. It's either free electrons or holes. So we either have an N-type or a P-type. There are two types of FET. We have a junction field effect transistor called a JFET, and then we also have the metal oxide semiconductor field effect transistor called a MOSFET. Field effect transistors are voltage controlled devices, meaning that an input voltage controls an output current. They have a very thin input impedance, thus they require very little power from the driving source. The two diagrams here show the construction of a JFET. On the left hand side we have the N-channel JFET, on the right hand side is the P-channel JFET. Let's look at the N-channel JFET. It has 4 leads. We have the drain, source and 2 gates, meaning that your current will be flowing from the drain through the N channel and then to your source. The gates on the side will explain as we move forward on what's their function. And then on the P channel, it means that your current is flowing through the P channel, which is made up of a P-type semiconductor material. JFETs and their characteristics. A JFET has 4 leads. It has the drain, the source, and 2 gates. The area between the source and drain terminals is called the channel. When the channel is N-type, the device is called an N-type JFET. Embedded on either side of the channel are 2 smaller P-type regions called the gates. When separate leads are connected to each gate, the device is called a dual gate JFET, commonly used in frequency mixers. In most cases, however, the gates are internally connected. So it means that you won't see the gates, you'll only see the drain and the source. The current flows between the drain and the source terminal in a JFET. For the N-channel JFET, the majority current carriers in the channel are free electrons because it's made up of N-type semiconductor material. For the P-channel JFET, the majority current carriers will be holes. Schematic symbols. Figure A shows us the N-channel symmetrical JFET. B shows us the P-channel symmetrical JFET. Number C shows us N-channel asymmetrical JFET. The difference between A and C, look at the gate. Where is the gate connected? In A, it's connected in the center. In C, it's connected towards the source. That's called asymmetrical JFET. Schematic symbols. When the gate regions of a JFET are located in the center of the channel, the JFET is said to be symmetrical. The drain and the source leads may be interchanged without affecting the operation of the circuit. So you can connect the positive or the negative voltage source. It will not change anything in the circuit. If the gate region are offset to the center, the JFET is called asymmetrical. The drain and the source leads may not be interchanged. Note that when the gates are offset the center in an asymmetrical JFET, they are placed closer to the source terminal. Current flow in the N channel when the gates are open. So you'll supply a voltage source across the drain and the source. That's called VDD. It's a voltage across the drain and the source. The gates, when the gates are open, that's when you'll have a current flowing in the circuit. JFET operation. With gates disconnected, the amount of current flow depends on 2 factors. The value of the drain source voltage, VDS, which we get from our supply voltage VDD, and the drain source resistance, RDS. The ohmic value of RDS depends on the following properties of the channel: the doping level, how much was this N channel doped, the cross-sectional area, and the length. In this figure, the electrons flow through the channel from the source to the drain because the drain is made up of positive relative to the source. In a JFET, the source current IS and the drain current ID are the same. Mostly, therefore, they are considered to be ID. So here we don't have current on the gate, so the current that's coming in to the drain is the same current that is leaving the channel through to the source. Gate action. What is the effect of gate on drain current? Figure A shows us the gate leads when they are shortened to the source. Figure B shows us the external gate bias reduces the drain current. Gates help in control of flow of current. In figure A from the previous slide, VDD was reverse biased both the PN junctions resulting in zero gate current. For a symmetrical JFET, the source distribution makes the width of the depletion layer wider near the top of the channel and narrower at the bottom. The current flows between the depletion layers and not the depletion layers themselves. Due to the different doping levels, depletion layers penetrate deeply into the channel and only slightly into the P-type gate region. Figure B shows how N-channel JFET is normally biased. The drain is made positive relative to the source and the gate is made negative relative to the source. The negative gate voltage depends the negative gate voltage expands the width of the depletion regions, which then narrows the channels. The narrow channel means reduced drain current ID. So we have a smaller current ID. By varying the gate source voltage VGS, ID can be controlled. When VGS is made negative enough, the depletion layers touch, pinching off the channel. This results in a current ID to be zero. The amount of VGS required to reduce ID to zero is called the gate source cutoff voltage, VGS off. The polarity of the biasing voltages for a P-channel JFET is opposite from that of a N-channel JFET. Shortened gate source junction. Figure A shows us a circuit whereby we have VDD that is applied across the drain and the source, giving us the voltage drop VTS. And then we also have VGG, a negative VGG that is applied on the gate, which controls the drain current because of this negative VGS. On figure B, we have the curve showing us the relationship between ID and VTS. And then on number C, it shows us the relationship between VGS and ID. When VGS is equal to 0, we get maximum ID, which is IDSS. As we supply negative voltage VGS, we have a lower value of ID until ID is 0. So the value that will cause ID to be 0 is called VGS off. When VGG is equal to 0, the gate is effectively shorted to the source and VGS is equal to 0. Figure C above shows the graph of ID versus VDS for this condition. The maximum ID that a JFET can have occurs when VGS is equal to 0. This is called the drain source current with the gate shorted, IDSS. As VDS is increased from 0, ID increases proportionally. When VGS reaches the pinch-off voltage VP, ID levels off. VP is the border between the ohmic region and the current source region. This is shown in figure A. The region below VP is called the ohmic region because ID increases in direct proportion to VDS. The region below VP is called the ohmic region because ID increases in direct proportion to VDS. The above VP is the current source region where ID is unaffected by changes in VDS. ID levels off above VP because the channel resistance RDS increases in direct proportion to VDS. JFETs are often referred to as normally on devices because ID flows when VGS is equal to 0. Drain curves. This is the graph of ID versus VDS. So we get the maximum IDSS when VGS is equal to 0. As we apply a negative voltage, VGS minus 1, then our ID value drops. We have a lower value of ID, VGS minus 2, ID is less and less until we get ID of 0. This is when we supply minus 4 in this circuit. So it means that minus 4 is our VGS off. Is the voltage that would cause ID to be equal to 0. Note the following, that VP is equals to minus VGS off. As you saw in the previous example, VGS off was minus 4, meaning that VP was equals to positive 4. The slope of drain curve in the ohmic region decreases as VGS becomes more negative because RDS increases. This allows using the JFET as a voltage variable resistance. The VDS at which the pinch-off occurs decreases as VGS becomes more negative. VDS peak is equals to VP minus VGS, where VP is the pinch-off voltage at VGS equals to 0 and VDSP is the pinch-off voltage for any value of VGS. Transconductance curve. A transconductance curve is the graph of ID versus VGS for a JFET. The graph is not linear because equal changes in VGS do not produce equal changes in ID. So in this example, the maximum current was 10 milliamperes. As we supply negative VGS minus 1, it gives us 7.5 milliamperes as our maximum voltage. When it's minus 2, it's around 4 milliamperes. For minus 3, it's less than 1. For minus 4, ID is equals to 0 because minus 4 is our VGS off. Calculate the drain current given IDSS and VGS off. ID can be calculated as follows as long as VDS is equal to or greater than VDSP. So ID is equals to IDSS open bracket 1 minus VGS over VGS off squared. When VGS is below VDSP, the formula does not apply, and JFET must be considered as a resistance RTS on. Example, in figure 30A, calculate the drain current ID for the following values of VGS. VGS equals to 0, VGS equals to minus 0.5, minus 1, minus 2, minus 3. We assume that VDS is equal or greater than VDSP. Determine ID for the following VGS values. So when VGS is equals to 0, ID will be equals to IDSS, which is 10 milliamperes in this case. So we used the formula ID equals to 10 milliamperes open bracket 1 minus VGS over VGS off. So when VGS is equals to 0, it would be 1 minus 0. So that is 1 times IDSS. That's why we got the 10 milliamperes. So when it's 0.5, it will be 10 milliamperes open bracket 1 minus 0.5 divided by minus 4. So this gives us 7.65. The calculations for C, D, and E. So for C, when VGS is equals to minus 1, so it will be minus 1 divided by minus 4. So 1 minus that, it gives us 0.75 squared times 10 milliamperes, giving us 5.62. For minus 2, it gives us 2.5. For minus 3, it's 0.625. So as VGS becomes more negative, the value of ID becomes less and less until it's zero. It's zero when we reach VGS off. JFET biasing techniques. In all JFET biasing cases, the gate source junction is reverse biased. The common biasing techniques include gate biasing, self-biasing, voltage divider biasing, and current source biasing. We start with the gate biasing. A negative voltage is applied through the gate resistor RG, as seen in the figure on the right hand side. Since there is zero current in the gate leads, the voltage drop across RG is zero. The main purpose of RG is to isolate the gate from ground for AC signals. Figure B below shows how an AC signal is coupled into the gate of a JFET. Okay, here's figure B and C showing us how the AC is coupled into these circuits, but for this level we don't have to worry about that part. If RG were omitted as figure C, no AC signal will appear at the gate because VGG is at ground for AC signals. The input impedance is Zin is very high and Zin is equals to RG. VDS is calculated as VDS equals to VDD minus ID RD. Remember, VDD is our supply voltage. We have a voltage drop on the resistor RD, and we also have a voltage drop between the drain and the source. So meaning that VDD is equals to IDRD plus VDS. That's how we got this formula. Gate bias is rarely used because of the characteristics of the individual JFETs vary over a wide range. Thus, for some circuits, the amount of VGS applied to a JFET may provide a very large ID, whereas other circuits, the same VGS reduces ID to nearly zero. Okay, on this example, assume that the JFET circuit in this figure is said to be mass produced. The JFET has the following parameters. IDSS minimum is 2 milliamperes, maximum is 20 milliamperes. VGS off minimum is -2, maximum is -8. For a range of JFET parameters shown, calculate the minimum and maximum values for ID and VDS if VGS is equals to -1.5 volts. Begin by calculating ID and VDS using the minimum values for IDSS and VGS off. So ID would be equals to IDSS 1 minus VGS, which is -1.5, divided by VGS off, which is -2. Then square bracket. This gives us 1.25 microamperes. Now calculate VDS. VDS we said is equals to VDD minus IDRD. So this gives us 19.875. ID equals to IDSS 1 minus VGS over VGS off. Now we're using the maximum values. -1.5 divided by -8. We get 13.2 milliamperes. VDS is calculated as 20 minus 13.2 times 1K. We get 6.8. Using the formula in 30, the following values of VDSP can be calculated. VP minus VGS, 8 minus 1.5, it gives us 6.5. This means that VDS is high enough to operate the JFET in the current source region. If VDS is less than VDSP, then the JFET no longer operates in the current source region but on the ohmic region. Under these circumstances, the value of RDS on must be known to calculate ID and VGS accurately. Self-biasing. So here we have a resistor or RS connected in the circuit. and we do not have VGG supplied to the circuit. Figure A shows us the self-biasing circuit and B shows us the transconductance curve. This is one of the most common ways of biasing a JFET. It uses only one power supply, FET. The voltage across RS provides the gate source biasing voltage. When the power is first applied, ID flows and produces a voltage drop across RS. Because there is no gate current, Vg is equal to 0. Therefore, Vgs is calculated as follows. Vgs will be equal to Vg minus Vs. Then that's equals to Ig Rg minus ID Rs. Remember, we said the source current is equals to the drain current. That's why we say here ID times Rs. Now, because the gate current is 0, so it will be 0 minus ID Rs. Therefore, Vgs is equals to minus ID times Rs. Self-biasing is very stable because any increase in ID causes Vgs to increase, and increase in Vgs causes ID to decrease. Therefore, thereby offsetting the original increase in ID. Likewise, a decrease in ID causes VGS to decrease. Self-biasing calculations. For a JFET circuit to self-bias, RS must be carefully selected. Normally, the value of RS is chosen so that ID is equals to half of IDSS. To realize this, VGS must be a quarter of VGS off. The approximation provides reasonably accurate results. A convenient formula for determining RS is equals to minus VGS off divided by 4 divided by IDSS divided by 2, which equals to minus VGS off divided by 2 times IDSS. Now here we are given a circuit whereby VDD is equals to 10, RT is 1K, RS is 200, and we are told that IDSS is equals to 10 milliamperes and VGS is equals to minus 4. So here you have to calculate the value of RS. It will be equals to minus VGS off divided by 2 IDSS. So minus a minus 4 divided by 20 milliamperes gives us 200 ohms. So Q values of VGS and ID are shown in figure B. The values of ID and VGS on the transconductance curve are not exactly 5 milliamperes and minus 1 volts respectively, because RS equal to 200 allows a slightly more ID. Okay. On this example, IDSS is equal to 10 milliamperes, VGS off is minus 4. With Vs at approximately 1 volt, calculate the drain voltage Vd. Okay, ID is calculated as follows. Remember, ID is equals to Is. So we have Vs and we have Rs. So we can calculate what is Is. It will be Vs divided by Rs, giving us 5 milliamperes. And since Is and ID are equal, so it means that ID will also be equals to 5 milliamperes. To calculate Vd, we proceed as follows. Vd is equals to Vdd minus IDRd. Voltage divider biasing. The voltage Vg is calculated using the voltage divider formula. Vg is the voltage from the gate to ground, which is equals to the voltage across resistor 2. Resistor 1 and 2 are in series relative to VDD. So if you use the voltage divider equation, R2 over R1 plus R2 multiplied by VDD, that gives us the value of Vg. And then once we have Vg, we know that Vg is equals to VGS plus Vs. So Vs will be equals to Vg minus VGS. Since ID and Is are equal, then ID will be equals to Vs divided by Rs. Also, the drain voltage VD will be equals to VDD minus IDRT. Advantages of voltage divider biasing: it is more stable than either gate biasing or self-biasing. Drawback: the value of ID for a given value of VGS varies from one JFET to the next, making it difficult to predict the exact values of ID and VT for a given circuit. So we have an example here for voltage divider biasing, and we're told that VGS is equals to -1. Calculate VG, VS, ID, and VD. So we begin by calculating VG using the voltage divider biasing circuit. So R2 divided by R1 plus R2 times 15, giving us 3 volts. Then next we calculate Vs, which will be equals to Vg minus Vgs, giving us 4 volts. Then ID is equals to Is, so it's Vs divided by Rs, 5 milliamperes. Then we calculate Vd. Vd will be equals to Vdd minus IDRT. Current source biasing. The NPN transistor with emitter biasing acts like a current source for the JFET. ID is equals to IC, and IC is dependent on the value of VGS. So IC is equals to ID. IC will be calculated as follows: VEE minus VBE divided by RE. So in this example, we first calculate the value of IC, which will be equals to VEE minus VBE divided by RE. So 15 minus 0.7 divided by 2.2 kilo ohm gives us 6.5, which is the value of IC. And then our IC value is equals to ID. If it's equals to ID, what is the value of VD? VD will be equals to VDD minus IDRT. JFET amplifiers. JFETs are commonly used to amplify small AC signals. One reason for using a JFET instead of a bipolar junction transistor is that a very high input impedance Zin can be obtained. A big disadvantage, however, is that the voltage gain AV obtained with the JFET is much smaller. The following JFET amplifiers configurations are considered: common source, common gate, and common drain.